Okay, so today I want to continue with our discussion of Yang-Mills theory. In particular, what I want to do is just work out for you explicitly the Feynman rules for Yang-Mills theory, which is, I suppose, an in principle straightforward exercise given everything that we've done so far in this course. But it is a bit more complicated, and it gives us another chance to sort of practice understanding Feynman rules. And then, starting this class, but mostly next class, I'm going to work out what's probably the most important computation in Yang-Mills theory, and possibly the most important computation in quantum field theory. That is to say, the computation of the beta function for the coupling in Yang-Mills theory. This is, as I said, one of the most important computations we'll do in this class. In particular, we'll discover, as 't Hooft showed in the mid-70s, that Yang-Mills theory is asymptotically free. That is to say, it becomes very weakly coupled at high energies. That's an important discovery, a Nobel Prize-winning discovery. I was actually just thinking to myself that we probably covered about a dozen Nobel Prize-winning discoveries this class. That might be, except for a class in quantum mechanics, that might be as many Nobel Prizes as you can cover in a class, unless it's like some stupid modern physics class or something like that. Okay, so that's just a sort of perspective on where we're going. And maybe just I can spend a minute and talk more generally about our plan for the rest of the semester. So I'm going to be out of town next week, so I've arranged for 2 very exciting lectures for you. So this week we're going to discuss asymptotic freedom and the formal structure of Yang-Mills theory. Next week you're going to continue. Guy Moore is going to give a couple lectures. He's going to talk more generally about QCD, what we do and what we don't know about QCD. As I sort of mentioned already, because of asymptotic freedom, Yang-Mills theory is weakly coupled in the ultraviolet at very short distances. That's great. It means if you want to do high energy experiments, then you can study perturbative Yang-Mills theory. But the flip side of the coin of asymptotic freedom is infrared slavery, right? It means that at very low energies, Yang-Mills theory is strongly coupled. QCD is strongly coupled. That's why when we talk about quarks and gluons, those are the only things that you can see at very high energies, but at low energies we see very, very complicated bound states, the bound states of nuclear physics. It's why we don't see free quarks and stuff like that. The study of quantum field theories where you don't have perturbation theory as a tool, where you don't have Feynman diagrams as a tool, is a rich and interesting topic, but a much more difficult one. And so next week I've asked Guy to give you a kind of flavor for the subject. For strongly coupled gauge theory, he'll talk a little bit about quark confinement, which is a property that we believe is true of Yang-Mills theory of QCD at very low energies. But it's a much more nebulous subject and a much more difficult subject than the ways that we've been approaching quantum field theory so far in this class. So next week, to some extent, you'll get a lesson on the lore, a lesson on things that we believe are true but that we can't really prove. Okay? And then after that, we've got another 4 lectures left. And so what we'll be doing is a sort of introduction to, we'll put together all of the ingredients that we've gathered so far in this course to finally construct the standard model of particle physics. So I'll spend probably a week discussing Goldstone's theorem and the treatment of broken symmetries in quantum field theory before moving on to what's known as the Higgs mechanism, which is probably one of, or the most important ingredients in the standard model. It's also important in understanding superconductivity and the subject of broken symmetries more generally. And finally, we'll end with a final discussion and a construction of the standard model of particle physics. Okay. So that's just sort of a overview of where we're going in this class for the next 4 weeks or so. But today, what I wanted to do is just go ahead and begin our more detailed study of the perturbative structure of Yang-Mills theory. Okay. So let me remind you of where we left off last class. Okay. So what we concluded last class is that when we study Yang-Mills theory, by computing, say, a scattering amplitude, if we wanted to do that using the path integral approach, then you would need to take care that you don't overcount your degrees of freedom by failing to account for gauge invariance. In particular, when we compute this partition function, we have to fix gauge invariance. So in particular, under a gauge transformation, the gauge field A will transform by the addition of the total covariant derivative of the gauge parameter theta. And here, this covariant derivative is in the adjoint representation, so it's a d-dimensional representation if the number of generators of your gauge group is d. And so I've written out explicitly the indices A and B in the adjoint representation. And the way that we fix this gauge invariance is we introduce a gauge fixing function that depends on A that has the property that if you set it equal to 0, this completely fixes the gauge parameter theta. So that means that if you want to integrate only over 1A per gauge orbit, in particular if you want to include in the path integral only 1A, dividing out by the action of the gauge group, then what you want to do is insert a delta function. Oops. Okay. I don't know why a little flag appeared there. And I don't know how to erase it. Okay. We'll just cover it up there. Okay. You get a delta function that enforces this gauge fixing constraint. But we have to worry about the determinant, the Jacobian determinant that arises when we introduce this gauge fixing. And in order to compute that Jacobian determinant, we introduced some auxiliary fields called ghosts. So these ghosts have an index, which is a gauge theory index A. It runs from 1 up to D. And they have an action. And the action is determined by the condition that when you compute this path integral, you get precisely the one-loop determinant that arises from gauge fixing. So the idea is that the gauge parameter, that the gauge variation involves this covariant derivative, and then this gauge fixing constraint, so we're choosing some sort of Lorentz gauge condition where you fix the divergence of the vector field A, and then you get a Jacobian determinant, which is the derivative of G, the functional derivative of G with respect to theta. And to compute that determinant, we just introduce a new field whose kinetic term is precisely the operator whose determinant you need to compute. So this is the Fadeev-Popov procedure. It looks a little bit exotic now as I've phrased it in quantum field theory. This is nothing more or nothing less than the usual sort of Jacobian determinant that you're used to computing when you do finite dimensional integrals. The only problem is that we're now doing a functional integral, an infinite dimensional integral. And so the Jacobian takes a slightly more complicated form. So So actually one of the problems that I just handed out for you to do next week is actually just an exercise where you're going to use the Fadeev-Popov procedure in order to compute a simple or a more simple Jacobian determinant, now for a finite dimensional integral instead of an infinite dimensional integral. In fact, have you guys seen the Vandermonde determinant before? Ever seen that? Okay. If you've ever studied matrix integrals or the theory of random matrices, this is a fundamental object that appears. It's a Jacobian determinant, and what you'll be doing on your problem set is computing a usual, a finite dimensional Jacobian determinant using this Fadeev-Popov procedure. Good. So there's one final simplification that I want to make when I do this. So when I introduced this gauge fixing procedure, I had this function omega a, which is some function of space-time. Rather, it's a set of d functions of space-time because it has an a index. And in fact, I don't want my final answer to have some arbitrary function in it. So what I'm going to do is do a very clever trick. So I have here a formula for my partition function that depends on omega a. But the answer that you get can't depend on omega a at the end of the day, right? Because the whole point of that Jacobian determinant is that it ensured that the answer that you get for the partition function doesn't actually depend on the functional form of g. G is just some intermediate object that you introduce in order to enforce some gauge fixing constraint. So what I want to do is I want to then integrate over a, and I'm going to integrate over a including a measure factor. And I could include whatever measure factor I want, because at the end of the day, the expression that I have for the partition function doesn't depend on omega a. So in particular, what I want to do is I want to take my expression for the partition function, and I'm going to integrate it with a measure factor, which is just a Gaussian measure for the function omega. And remember, this gets multiplied by the gauge fixing delta function, which if we write it out explicitly is omega a minus d mu a. So what I want to do is I want to just take the expression that I have for the partition function and integrate over omega with this measure factor. I could have chosen any measure factor I like. I'm just going to choose this measure factor, and I have introduced a parameter that I've called psi here that labels different choices of measure factor, and at the end of the day the answer is going to be independent of psi. And when you do this integral, what do you get? Well, you get some function of a. And what is that function? Well, it's a new contribution to the action that depends on our choice of how we fix the gauge invariance. And if you just stare at this integral for a second, well, it's very easy to do. It's the integral d omega a, but we have a delta function that fixes omega a, so we use the delta function to do the integral. Now here we have an infinite number of delta functions that we're using to do an infinite dimensional integral, a functional integral, but the idea is the same. And what do you get? You just get a gauge fixing action, which is 1 over 2 times psi times d mu a squared. The result being that if we make this simplification, our gauge theory partition function now involves an integral over gauge fields, as well as over ghosts C and C bar, of an action, which is the Yang-Mills action, plus a ghost action, plus a gauge fixing action. Okay. And we see that the result of this little trick where I integrate over omega is just that I've added an additional term to the action to fix gauge invariance. So I want you to remember back to our discussion of electromagnetism, where we talked about arc psi gauge and electromagnetism. And we concluded that one simple way of enforcing arc psi gauge was just to add another term to the action. And what was the term that we added? Well, it was exactly this term here. So all I've done is come up with a slightly more sophisticated way using this Faddeev-Popov procedure of introducing that gauge fixing term. Question?
Is the A in the measure factor impacted with the A in the sequence?
The A in the measure factor, so you don't contract the index in the measure factor with anything. If I understand, you're talking about like this measure factor here, or something like that.
Oh, I'm sorry. I meant the A index on the omega.
The A index on the omega. Yeah. Remember when you when you have an index, let's put it this way. You don't integrate over, you don't contract an index of an integration measure, right? So for example, if you were doing an n-dimensional integral and you wanted to integrate over, dx1 up to dxn, you could schematically write this as the integral dxi. I guess you would really write it as that, product over I dxi. And so when I say integrate over omega A, what do I mean? I integrate over omega 1, and then over omega 2, and over omega 3, and over omega 4. So I should really, when I write an integral d omega A, what do I really mean? I really mean a product over all points x in space and values A of that index of some finite one-dimensional integral. Is that clear more? Is that clear more?
Yeah,
or less?
sorry about that.
Yeah. No, it's fine. There's a lot of indices floating around. That's an important point, though. Good. Any other questions? Okay. So it's now, I guess, an in principle straightforward exercise to write down the Feynman rules. But it's one that I want to go through because it turns out that the Feynman rules for Yang-Mills theory are a bit more complicated than they are for the other sorts of quantum field theories that we've written down. And it's simply because there's just a lot more terms involved. As you discovered when you were working out the Yang-Mills theory, Lagrangian and gauge invariance and stuff like that, there's a lot of terms and there's a lot of indices that need to be treated carefully. So, but now what I want to do is I want to work out the Feynman rules. Now, previously, when we've discussed Yang-Mills theory, I've used the sort of geometric normalization where the kinetic term has a 1 over g squared in front of it. But just for the sake of making perturbation theory a bit more clear, what I want to do is change the normalization factor so that I don't have that 1 over g out front. All that means is that I take A and I multiply it by a factor of the coupling. That means that every time you have a covariant derivative, d mu is d by dx mu plus a mu. You now get a d by dx mu plus the coupling times a mu. Okay? And the reason why I want to do this is that this makes the perturbative expansion, the expansion in powers of g, a little bit more clear. So let's see why that is. So first, let's just consider the action for the gauge field. Okay. And let's include the gauge fixing term here as well. So what is that? Well, you have f mu nu, which is d mu a nu minus d nu a mu, plus plus a term involving the structure constants, f a, b, c. So that's f mu nu a. And then we have a similar term here, where we have an upper index, mu nu contracted with it, and we also contract the a index. And then we have this gauge fixing term, which is also quadratic in A. And then, if you want to work out the Feynman rules, all you need to do is expand this out, and you'll get, for example, a term which is quadratic in A. So here, let's just work out the term that is quadratic in A, coming from taking this guy and multiplying with the appropriate term that's linear in A over here. So we can then, let's see, we can integrate by parts and write this as the sum of two terms. You get a g mu nu times d by dx squared minus d mu d nu acting on a nu a. Okay. So that's just what you get if you take this term and contract it with an analogous term over here. So as you can see, the reason why there's two different tensor structures that appear. There's one tensor structure where this a index here is contracted with an a nu up here. So let's just write that out a little bit more explicitly. We get a d mu a nu a minus d nu a mu a. So there's one term, for example, where this nu index is contracted with that nu index, and the two derivatives are contracted with one another. And then I've integrated that by parts to get a d squared here. And then there's another type of term where, say, the derivative operator here is contracted with the nu index on A right there. And that gives you terms with a tensor structure that looks like this. And similarly, you also get a kinetic term from the gauge fixing term, which, if we integrate it by parts, looks like this. Sorry, I guess I didn't contract my indices very well. Okay, that should be an upper mu index. Let's just be careful about our Lorentz indices. Okay, so that wasn't too bad. All I've done is write out the term that's quadratic in the A's. And I've integrated it by parts so that it looks like A times differential operator on A, so that the Feynman rules will just involve a propagator, which is the inverse of that guy. So next we get terms that are cubic in A. So for example, if you take this term here and contract it with this term here, what do you get? Well, you get something, you get an A mu A nu B times D mu A nu C. So this will be some three-point coupling between three A's that is proportional to the structure constant. And in writing this guy down, I'm freely using the fact that, to make life simpler, the structure constants are completely antisymmetric. So you can always reorder them at the cost of introducing a minus sign every time you swap two of the structure constant indices. So for example, that means that this term and this term both combine into the same term, which cancels one of these factors of 2 here, And then there's another term here involving an FAA that contracts with those terms to give you another factor of 2. And then finally, you have the terms that involve no derivatives and 2 copies of the structure constant. So these give you an interaction that is quadratic in the coupling constant G, and you get an FABC, FCDE. So 2 of those gauge couplings have to be contracted with one another because you have an FABC here and an FA, I guess you would call it DE there, and you'll get A mu A nu B, A mu C, sorry, D, A nu E. And all you need to do is you need to be a little bit careful about how these various Lorentz indices and structure constants are contracted with one another. So for example, yeah, okay, so is that more or less clear? Any questions on that so far? So from this, for example, we can read off the propagator. So the gauge boson propagator can be most easily written in momentum space. Remember, the propagator is the operator that inverts the kinetic term in the Lagrangian. And here I've written everything in position space, but it's easier in momentum space. So what is the propagator? Well, it'll have an A and a B index, and a mu and a nu index, right? Because now we have one gauge field for each value of the Lorentz index mu, as well as for each value of the gauge index A. And the propagator is diagonal in the gauge index. We can just put a delta AB there. And then it'll take, actually, exactly the same form for the propagator of a U1 gauge boson. So this is just, all I've done here is rewrite this term right here. And then we have the contribution from the gauge fixing term. And of course, the result at the end of the day, just as in quantum electrodynamics, better be independent of our choice of gauge fixing term psi here, as long as you're careful to use the same gauge in every different propagator that you use in a particular computation. So, for example, if we want to make our life simple, we could just set zeta equals 1, or psi equals 1, and that's a particularly simple gauge known as Feynman-Tuft gauge. It was called Feynman gauge in the case of electromagnetism. Now it's Feynman-Tuft gauge. More generally, as in the case of electromagnetism, you could keep track of the powers and factors of psi that appear here, and this would be called arc psi gauge. Any questions on that? So far, nothing too complicated. Let's now talk about the three-point function. So, okay, so the first thing that I should mention is that in the language of Feynman diagrams, this propagator is just represented by a squiggly line, and we just need to keep in track of the fact, or remember the fact, that you now have a pair of indices at each endpoint representing the different labels for the gauge field, one Lorentz index and one gauge theory index. Any questions? Okay. Now, how about the three-point interaction? Well, the three-point interaction comes from this term right here. This guy is now labeled by 6 indices. a Lorentz index and a gauge theory index for each endpoint. And because we have a derivative here, your interaction vertex is going to depend on the momenta of the gauge bosons. And I'll call the momenta of those three gauge bosons P, Q, and R. And what will you get? Well, if you just read off from this term here, you'll get an I, because it's an interaction vertex, a factor of the coupling, G, times the structure constant. And then you get, just looking at this interaction vertex, minus, you get 1 power of momentum. So let's say that we're looking at this gauge boson here, which has momentum R. So you'll get an R mu, or an R, did I do that right? And it'll be an R rho, sorry, I've mistaken my notes, times a G mu nu. Did I get that right? Yeah. And then you have the various other permutations. So you get 5 more permutations for a total of 6 terms, 6 being the number of permutations of 3 objects. Okay, the number of orderings of the 3 endpoints. Okay, now you can write all of these permutations out and do some simplifications. I won't bother to do it for you explicitly. I'll just tell you what the final answer is. And this answer can be simplified somewhat using the fact that momentum is conserved, so that P plus Q plus R is equal to 0. So the final answer that you get, those 6 terms, can be combined into 3, which I'll just write down for you. So the answer, once you sort of write down one term, can be completely determined just by using the fact that your answer has to be invariant under the permutations of the 3 legs. So here I've just written it down for you. I suppose it wouldn't be too hard to work it all out explicitly, just for the sake of making life easy. I just told you what the answer is. It's just some straightforward simplification. And finally, there's going to be some 4-point interaction. This is the interaction where gluons or gauge bosons bounce off of one another. So now we have 8 indices. And so what do you get? Well, you can just read it off from this term here. Just stare at that term here. So you have an FAB here. I'm going to write it a little bit differently because I called my free indices A, B, C, D here, whereas above I'd summed over C, so C was my dummy index. So I'll write this, so you get a factor of I and a G squared. I'll write this as F, A, B, E, F, C, D, E. So what I called C in this expression here, I'm calling E below, in order to make my free indices A, B, and C, rather than A, B, D, and E. And then these A, B indices match up with those 2 Lorentz indices. So you get a G mu nu, G rho sigma, plus various permutations. The only thing that one needs to keep track of here is that the indices match up. So here, the A and B here match up with the mu and nu indices here. Is this clear, more or less? I mean, it's a bit of an exercise in keeping track of indices. Again, if you write everything out and use the anti-symmetry property of the structure constants, you can make your life a little bit simpler. So here, I'm just going to write down the answer for you. I'll try and do it a little bit more quickly, just because I don't know how illuminating it is. But you get a G mu rho, G nu sigma, minus G mu sigma, G nu rho. So that's two of the possible permutations. And then you get various other terms. So these corresponded to the terms where you had an A matching up with a B and a D matching up with a C. But now you have other terms where, say, an A matches up with a C. So you get FACE, FBDE times G, let's see. I get this today. Let's see. I want to make sure that I got, what did I? Oh, I'm sorry. We have to be careful here. Okay, I have some typo in my notes. So, rather than, okay, there we go. Rather than boring you guys by writing down the next 8 terms that appear here, there are 8 terms, in addition to the 2 I've written down here, sorry, 6 terms. I'm just going to write ... okay? Maybe this could be an object lesson, that you need to be incredibly careful with your indices when you write out even the interaction vertices in Yang-Mills theory. I appear to have made a little, okay, I've made a little mistake when I wrote these down in my notes, and I don't want to propagate that mistake. So I'll just tell you that if you need to work out this interaction vertex, well, you could work it out yourself just by adding up the various permutations here. Or you could look it up in the textbook, where it's written out quite clearly. But the object lesson here is that there are lots of terms. And this makes the computation even of tree-level scattering processes in Yang-Mills theory very complicated. Much more complicated than you might naively expect. Because you have all of the different ways that these Lorentz indices and group theory indices can be contracted among one another. So, for example, let's say you want to calculate gluon to gluon scattering. So if you want to calculate gluon to gluon scattering, those are supposed to be gluons there. Sorry, the line's not curly enough. Just at tree level, what do you get? Well, you have a 3-point interaction, like that. Plus, you have a 2-to-2 interaction. And both of those terms are of order g squared. So they both arise at the same order in perturbation theory. And then it turns out that if you want to calculate this thing and you want to average over the final spins and the final colors, and you add in all the various terms that appear here arising from permutations, they're actually around 13,000 terms. Whereas, well, when you did this in electromagnetism, well, there were 0 terms, okay, because the electron doesn't couple to itself. And even in QED, there was 1 term. Okay? Maybe there are a few more terms if you add in a polar. Well, no, actually, even if you do the polarization sums, it's pretty trivial. You just do the polarization sums. Sum epsilon mu star is g mu nu. But because of all the various ways that you can contract these group theory indices, when you add them in Yang-Mills theory, even tree-level diagrams in Yang-Mills theory are completely horrible. Okay? And so it's actually a kind of interesting lesson that even tree-level Yang-Mills theory The Feynman diagram expansion, although perfectly technically correct, there's no worry about non-perturbative effects or anything like that, is a very, very inefficient way of proceeding. And it actually turns out to be a very interesting subject of current research, whether there are more efficient ways of organizing tree-level Yang-Mills scattering amplitudes. So in fact, probably one of the most interesting developments in the subject of quantum field theory in the last, let's say, 5 years, has been the development of new sets of techniques that replace the usual Feynman diagram expansion for Yang-Mills theory that allow us to compute all of these terms much, much more efficiently. So, there are ways of reorganizing the Feynman diagram expansion, even at tree level, which replace these thousands of terms, or in many cases millions of terms or billions of terms, by one term or two terms or three terms. And this sometimes goes under the name of the spinor helicity techniques in Yang-Mills scattering amplitudes. One of the things that I think is truly remarkable is that these are not fancy. This is nothing fancy that I'm writing down here. This is tree-level Feynman diagrams. It's tree-level. It's classical physics. Okay? There's no quantum mechanics. There's no loops. There's no nothing like that. All it is the fact that the Feynman diagram language in gauge theory is perfectly correct, but it's just not a particularly efficient way of keeping track of your results. So, for example, when you add up these 13,000 terms, if you add up 13,000 random terms, you might expect that the answer that you get is very complicated. But in fact, it's a very simple answer. It's done, and I think it's even done in some of the textbooks, and it's something you can write down in one line. And so generally, if you have a problem where, in physics, where the statement of the problem is simple and the answer is simple, but the intermediate steps involve 13,000 terms that you have to add together that all cancel and combine together in miraculous ways, that usually means you're missing something. And so that's sort of the idea of these spinor helicity techniques. Is they allow you to organize things so that all of these cancellations occur in intermediate steps of the calculation. So that's really not something that I think we're going to talk about too much this semester, but I just wanted to bring it up because I want to emphasize that, I guess as we've already mentioned even this lecture, Yang-Mills theory is a very deep subject and not one that I think is completely well understood. I mean, we have Feynman diagram techniques. They work great for the computation of certain things. But in other cases, I think new tools are still being developed. Okay, question, yes?
When, if ever, do we have to use or think about ghostly Feynman?
Yeah, that's coming next. Okay, good. So, as we've seen, in order to calculate the one-loop determinant that appeared in the path integral correctly, we needed to introduce these ghost fields. These ghosts, I argued, were necessary for the theory to be gauge invariant, so that the exact form of the gauge fixing term doesn't enter into our answer. And so that means that at higher orders, so beyond tree level, you must include ghosts in order for your answer to be gauge invariant. So why don't you need them at tree level? Okay, well, one of the things that we discussed last time was the fact that these ghosts are not physical states. They only appear in internal in the Feynman diagram. If they were external states, then they would violate spin statistics, for example. And if you think about it, that means that because ghosts can only ever appear, they can't ever appear as external states, ghosts can only appear in loops. Okay? So the effect of ghosts will only be important if you're studying the physics of loop effects. So for example, when we calculate the beta function of Yang-Mills theory, ghosts will be important. So remember that the ghost Lagrangian, well, it was minus, well, the sign isn't actually even so important because it will cancel out in loops. So you have a kinetic term, and then you have an interaction term, which describes the interaction of these ghosts with a gauge field. And so these lead to a propagator that has two indices, which in momentum space we would just write as 1 over k squared with an appropriate I epsilon term. Or in the language of Feynman diagrams, if we represent a ghost by a dotted line, then we just need to remember that there's an A and a B index at each end of the line, reflecting the fact that we have to keep track of the different species of ghost labeled by that group theory index. And there's a momentum K, and because the ghosts are complex fields, they carry charge, just like electrons in QED. I have to draw an arrow on the Feynman diagram as well to tell you what direction charge is flowing. And there's also going to be an interaction vertex. If there weren't, then we wouldn't need to care about the ghosts, just as we didn't care about ghosts in electromagnetism. And this interaction vertex, let's see, we'll write the gauge theory index with an A, and so I'll write these with a B and a C. So what is this? Well, we have one derivative here. Now, where you put the derivative depends on some integration by parts. You know, I've written it here with the derivative on the C bar term. So that means that because it's a C bar, this is the outgoing state. So if we call the momentum of that outgoing ghost Q, you get an interaction vertex, which is the structure constant FABC, times, well, you have the derivative of that guy. The derivative is minus I times the momentum operator. So that's G times FABC Q mu. And finally, of course, Yang-Mills theory is only interesting, or most interesting, if we have matter fields. So let's also consider fields that are charged under the gauge bosons, such as quarks, so what is the Lagrangian describing those quarks and their coupling to the Yang-Mills field? Well, this is just the kinetic term that we've written down several times before. So here, maybe what I'll do, just to make things a little bit more clear, is I'll write out the index I that labels the different fields in a representation of the Yang-Mills gauge group. So the kinetic term is just the covariant derivative d slash plus m. And here I'm multiplying the m times the delta ij, just because I've written out the representation index explicitly. So if you wanted to write this out in a little bit more detail, you would expand out that covariant derivative, and you get a psi bar I times d slash plus, that's d slash minus m, of course, is the Dirac field kinetic term. And then you have a coupling term coming from the covariant derivative that's proportional to the gauge coupling G. You get an A mu A times psi bar I gamma mu, that's because of the slash, times the representation matrix Tij. Is that clear, more or less? This is exactly the same coupling that you have in quantum electrodynamics, except that instead of the electric charge E, you now have the gauge coupling G times the representation matrices Ta. You probably wrote this out explicitly on the problem set due today. Any questions on that? Okay, so now it's straightforward to go ahead and write out the Feynman rules involving this Dirac field. So here the propagator is just the usual propagator. Of a Dirac field. I just need to take into account the fact that I now have an extra index that labels the different size in this representation. But, of course, that index just goes along for the ride when we're talking about the propagator, okay, because the index I here is just contracted with that index I. So the propagator for the spin 1/2 field is exactly the same as it is in quantum electrodynamics. Nothing too fancy going on there. The interesting thing is the interaction vertex. Sorry, let me rewrite that a little bit. Which again takes a form that's very similar to its form in Yang-Mills in electrodynamics, except that now you've got a representation theory matrix. Now remember here, this guy has, the gauge boson has a Lorentz index mu and a group theory index A. The Dirac fields have representation indices I and J, as well as Dirac spinor indices that I haven't even written down here. Okay. So although this is a relatively simple expression, let's see. I mean, just for fun, we could count up the number of terms that actually involve. You have 4 Dirac indices for each of the Dirac fields. You have 4 gauge theory indices, so altogether that's 64 indices. And then, let's say, I don't know, you're doing SU3, and the quarks are in the fundamental representation. So then A runs from 1 up to 8, okay? And then each I and J takes one of 3 values. So you have 64 times 8 times 9. Okay, that's a pretty big number, whatever it is. So, you know, I mean, indices are good, right? And if you can suppress your indices, that's even better. Okay. So here I've written down the interaction vertices and the Feynman rules for fermions. It's a reasonably straightforward exercise, and one that you'll do for next week, to write down the Feynman rules for scalars, transforming into an arbitrary representation of the gauge group. It's very, very similar to what you do when you study scalar quantum electrodynamics. The only difference is that you now need to be a little bit more careful to keep track of the various group theory indices. And as in scalar quantum electrodynamics, instead of just having a cubic interaction vertex where you have, say, 2 electrons going to a photon or 2 fermions going to a gluon, you now have a 4-point vertex when you have scalar fields, just because you have two covariant derivatives. So you have a term involving phi squared times a squared. So on the problem set next week, you'll work that out explicitly. Okay. Are there any questions before I continue? Okay. It's a sort of sad fact of life that computations in Yang-Mills theory are so much more technically complicated than even in QED. Who knows, maybe one of you will discover the vast simplification that makes all of our lives much easier. Or maybe it's only complicated because we're not used to it as much. So what I want to start doing now is I want to describe what's perhaps the most important computation in Yang-Mills theory, which is that of the running of the gauge coupling, that is to say the beta function for the coupling constant G. Before I dive into the direct coupling computation of this beta function, maybe I should just set the stage a little bit and remind you of how things worked in quantum electrodynamics and exactly how it is we'll be doing the computation in Yang-Mills theory. So remember, in quantum electrodynamics, we studied the vertex where you have the quantum corrections, the loop corrections, to a vertex where you have, say, two electrons coupling to one photon. And we found that whereas at tree level that was just a number, it was the gamma matrix, once you start including loops, it had a dependence on momentum. And that could be understood as the fact that the effective electric charge had a dependence on energy. And in particular, schematically, this is reflected by the fact that in quantum field theory, the vacuum of empty space is a kind of dramatic and exciting place. And so that if you put a charge, say, at the origin, and you have a quantum field theory that allows for the creation of virtual electron-positron pairs, then that charge will be screened in some way. So for example, if an electron has negative charge, it will want to be screened by a collection of dipoles, electron-positron pairs, which partially screen the electric charge sitting at the origin. And that means that as you probe the theory at higher and higher energies, you're effectively getting closer and closer to the electron at the origin, because you're probing at shorter and shorter distances. And so the strength of the electric charge increases. So in QED, the electric charge becomes large at high energies. And this reflected the fact that, well, in quantum field theory, there's charged matter that fluctuates, and so electric charges will be screened at long distances. What we're going to find is that in QCD, and in particular in a wide variety of Yang-Mills theories, what we're going to find is that essentially the gauge coupling can become weak. That is to say, the gauge coupling can become small at high energies. Now, whether the gauge coupling becomes small or weak depends on what sort of matter there is in the theory. So, for example, we saw that with electric charge, the fact that there was, virtual electron-positron pairs that appeared in the vacuum essentially screened the electric charge. so that it become weaker at large distances. Now, in a gauge theory, so now you might ask how it could possibly be the case that in a gauge theory, that in any sort of theory where you have charged matter, you could have screening which makes the charge stronger at long distances rather than weaker at long distances. You know, I've drawn a very intuitive picture here about how it is that the effective charge of an electron can become weaker at large distances because of screening. Somehow in gauge theory, the magical thing that happens is that there's anti-screening, so that charges effectively become larger at long distances rather than smaller at long distances. And the point is that in Yang-Mills theory, we don't just have charged matter fields, but the gauge bosons themselves, the gluons themselves, have charge. What do we mean by that? Well, we saw already that there was a 3-point interaction vertex and a 4-point interaction vertex. So, for example, you know, the presence of this interaction vertex here, that reflects the fact that your fermion field has charge, but you also have this vertex here. Okay, that reflects the fact that a gauge boson has charge. It's a charged object. It transforms in a particular representation of the gauge group, just like your matter fields do. However, gauge bosons are slightly different than our usual matter fields because they have spin, and because they're in the adjoint representation of the gauge group rather than, say, the fundamental representation. And so all of that changes the way that gauge bosons screen charge. And in particular, gauge bosons, it turns out, anti-screen charge. So in a theory with only gauge bosons, so sometimes this is called a pure glue theory. That's a theory where you don't have any matter fields, you just got the Yang-Mills fields. Yang-Mills fields are called gluons because they glue the quarks together. And so a theory with only Yang-Mills fields is a theory of pure glue. Okay? That's at least what they call it. And in a pure glue theory, you only have anti-screening. Now, the question then of whether or not a given Yang-Mills theory has a coupling that gets weak at high energies or strong at high energies then depends on detailed questions like what is the gauge group and what sort of matter content do you have. So whether G goes to 0 at high energies will depend on the matter content. So the computation that I'm going to do is I'm going to compute various different, okay, that's not a fire alarm. I'm going to compute various different contributions to the beta function for Yang-Mills theory. And what we'll see is that depending on what sort of matter we have, what sort of gauge group we have, there are various different possibilities. And in some cases, the beta function is positive, meaning that the coupling wants to increase. So remember, the beta function is the change in the coupling with respect to your energy scale. In some cases, the beta function will be positive, and the theory will want to get stronger at high energies. And in other cases, the beta function will be negative, so that the theory will get weaker at high energies. And it's just a fact of life that in QCD, the theory of strong nuclear interactions, the beta function is negative. And so the coupling constant of QCD gets very weak at high energies and strong at low energies. Good. So that's the computation. What I think I'll do in the next 15 minutes or so is just set up the computation. it involves a lot of the sort of same kind of loop diagrams that we've computed already in this class, so I'm not going to do every single bit of the computation. Instead, what I'm going to do is just pick out those parts of the computation that are new, that involve the more complex group theory structure, just to sort of describe in a little, a bit more schematically how we do this computation. Maybe before I start getting into this, I can pause and see if there are any questions. The fact that gluons can anti-screen instead of screen is a kind of remarkable thing, and it's actually not so hard to understand. So if I have some time at the end of class next Thursday, maybe what I'll do is try and describe that a little bit more intuitively, because it is actually possible to get a kind of intuitive picture for why it is gluons can anti-screen charge rather than screen charge. Any questions? Want to continue? Okay. So the first thing that we want to remember is that coupling constants run. Coupling constants change with energy because of loop effects. Okay. And in particular, they change as a function of energy because of the various coupling constant renormalizations and wave function renormalizations that reflect how the different terms in the Lagrangian vary as you change your definition of the renormalized couplings. So let's just try and understand that a little bit more systematically. So let's imagine, so we have our Lagrangian. Okay, so it's the Lagrangian of Yang-Mills theory plus the Lagrangian of the ghost fields plus some gauge fixing term plus some matter terms. And we could think about this as written in terms of Baire fields, say A naught, C naught, and psi naught, where this naught refers to the Baire fields, and a Baire gauge coupling, G naught. And then we could rewrite this in terms of renormalized fields, what we usually call A, C, and psi, and the renormalized coupling, G. And when we do that, well, you get the action in terms of the renormalized fields plus some counterterm action. And it's probably worth just writing this all out a little bit more explicitly in the case of Yang-Mills theory. So for example, the renormalized action, so we would have a kinetic term, so d mu a nu minus d nu a mu squared. And then you would have some wave function renormalization that we called Z3 here, that just reflects the fact that order by order in perturbation theory, we set the pole and the propagator to have the appropriate, we demand that the propagator and momentum space have the appropriate pole and residue. And then we would have some wave function renormalization as well as mass renormalization for the matter fields, which I'll call Z2 and Zm. You'll also have some wave function renormalization for the ghost fields that I've called Z2C. Okay. The 2 here, well, I sort of made up this notation last night. Maybe it wasn't a very good one. the C here reflects the fact that it's a ghost, and 2 here I'm using to denote the fact that it's a matter field. And then we'll have some renormalization of the coupling constant involving A times psi squared But one of the things that is important to remember is that the coupling constant G appears all over the place in the Yang-Mills Lagrangian. So for example, there's one term here that I've called Z1 that involves the renormalization of that coupling constant term the A psi coupling. But G also appeared in, say, a 3-gluon term. So what was that? That was FABC times D mu A nu A mu B A nu C. So I'll call that wave function the renormalization of that term Z3G. And finally, there's a 4-gluon term which could get renormalized. And so that involved two structure constants, FABC, what did I call it? I think I called it FABE, FECD, A mu A nu B, A mu C, A nu D. And then finally there was a fourth place that the gauge coupling appeared. Sorry, and that was a G squared. A G squared times, we could call it Z1C because it reflects the gauge coupling between the gauge field and the ghosts fields. So an FABC, CA, C bar B, D mu A C. And the point is that there are really 4 different places in these interaction terms where the gauge coupling appears. And we should introduce counter terms for every interaction vertex. And so you'll have counter terms for each one of those 4 terms, which you could also rewrite as renormalizations of those 4 different couplings in the theory. So in particular, you could worry that this coupling, this coupling, this coupling, and this coupling all get renormalized differently. Yes, question.
Why do we have 4 different G's for the same G?
Okay, right. I mean, that's what I'm trying to explain. So, in principle, you could worry that you have different Z's for each G. But when we constructed our action using gauge invariance, all of the different coupling terms here were related to one another. So you know that if gauge invariance is preserved, order by order in our loop expansion, that all of the different terms here have to be related. Okay. So that's not something that I've proven to you, okay? But it turns out that it is a true statement. And basically what that statement reflects is the fact that, so let's, for example, imagine comparing this term to the one that appears in the Baire Lagrangian. So if you compared it to the one that appears in the Baire Lagrangian, then the Baire coupling would be equal to the renormalized coupling times a factor of Z1, that's this factor right here, and then you would have to account for the fact that each one of these fields picks up, the A and the psi fields each pick up wave function renormalizations. And so you would have a factor of Z2, which is the wave, you would have a factor of 1 over Z2, which is the wave function renormalization of the psi field, and the square root of Z3, which is the wave function of the A field. Right, so this term here, we're comparing that term in the renormalized action to the term in the Baire action. In the Baire action, you write everything in terms of the Baire fields. And by comparing, say, this term here to the action involving the Bayer gauge field, you see that A is the normalized gauge field A is related to the Bayer gauge field by a factor of the square root of Z3. That's where this guy comes from. And the renormalized matter field is related to the Bayer matter field by the square root of Z2. And then we had two psi's in this formula, so we had the Z2 down here. So for example, that's the comparison between the Bayer term and the renormalized term for this term here. We could also compare it, say, I don't know, to this term here. That's a nice one to compare because the formula is almost identical. What is it? It's G times Z1C divided by Z2C. That's this wave function or normalization here, times the square root of Z3. Or you could compare it to this term here, okay, or this term here. So let's take, say, this term right here. What do you get? Well, you get G times Z3G, and then you get three factors of the wave function or normalization for the A. Or finally, okay, I guess I've written down three of them. I might as well write down the fourth. You get a Z4G, now with a square root, because we had a G squared here, divided by Z3, which is the square root of the square root of the square root of Z3 to the fourth power. Okay, because I have 4 powers of A here. Okay. Right. Okay, so we know that if gauge invariance is preserved, these various wave function or normalizations must be equal. And this is actually something that is true in gauge theory. If you could compute these things order by order in perturbation theory and check it, say, at the one loop level if you like. There actually are more formal proofs of these facts. Sometimes these are known as the Slavonov-Taylor identities. They can be proved. This is very analogous to the proof of the Ward identities in QED, which is something that, well, I think we motivated and we checked in a couple examples in QED, but we didn't prove. And similarly, I think for the sake of sanity, I'm not going to try and prove any of these things in Yang-Mills theory. I'm just going to make these statements, and if you want to go look up the proof, it's sort of beyond, I think, what's in any of the textbooks, but I think it's something that you should certainly look up if you're interested in. But now we see that if you want to understand the beta function, then you just need to compute some of these wave function normalization factors. So for example, G naught is the Bayer coupling constant. It's independent of your normalization scale, obviously, because that's the definition of a Bayer coupling constant. So from that boxed equation, we have the beta function, which is the derivative of the coupling with energy with the renormalization group scale. So what is that? That's, well, d by d log mu of Z2 plus 1/2 Z3 minus Z1. Just taking the logarithmic derivative of that Fox equation. Okay. So here, the ZIs are computed in terms of some RG scale, some renormalization scale. That I guess I've called it mu in this formula. Okay. I mean, so this is something that, the fact that the beta function can be computed from the wave function or normalization or the coupling constant normalization, something that we've seen already, but I think it's always good to see again. And so what I'm going to do next class is start computing these objects and then assembling it all together to get the beta function. I'm just about out of time here, so maybe I can just see if there are any questions before we end for the day. Good. Okay, see you on Thursday.